All right, here we go, Math 2. Last lesson for tonight, and then I can go on Thanksgiving break. That'll make me happy. So we got lesson 4.1.4, factoring completely. All right, so to factor completely means when we factor, everything must factor so that it can't factor again. So we have to make it prime so that it can't factor any further. All right, so factor the following. Now, if we're factoring completely, the first thing that I want you to do is always look for a GCF first. So look for a GCF, see if you can find one, factor it out first. So does anything go into 9, 12, and 4? Well, 3 goes into 9 and 12, but 3 doesn't go into 4. And then 4 goes into 12 and 4, but it doesn't go into 9. So I'm not seeing a GCF there. Okay, so then I will proceed with the problem like I normally would. So I set this thing up and I put my 9x squared here and my 4 here. So multiplying those two together, I get 36x squared. And then they should add up to be negative 12x. All right, so I want something that multiplies to give me negative 36, but adds to give me negative 12. This one's a little bit tricky because we're multiplying and getting a positive, but adding and getting a negative. The only way that happens is if both of these numbers are negative. So I need two numbers that multiply to give me 36, but add to give me 12. And both of them are going to be negative numbers. And I just thought of it. It's going to be 6x and 6x. These two multiply to give me positive 36, but since they're both negative, they're going to add to be negative 12. So I'm going to put negative 6x here, negative 6x there. So I can't put 9 and 1, or 9x and 1x. So the only way to split it up is 3x and 3x. All right, so that makes this one negative 2, because 3x times negative 2 is negative 6x. And that also makes this one negative 2. So we get the same exact binomial on both sides. So we said this on a previous lesson. We can write this as 3x minus 4 times 3, or 2, not 4. 3x minus 2 times 3x minus 2. Or you can write it as 3x minus 2 squared. All right, next one, we talked about this on a previous lesson. We said if there is no m term in the middle, that means that it's adding up to be 0m. So setting this one up, I would put 81m squared here and negative 1 here. Okay, so multiplying those two, I get negative 81m squared. And then they should add up to be 0 because there's no m to the first term in there. And I can think of the numbers off the top of my head. I can see that this is going to be 9m and negative 9m. They multiply to give me negative 81m squared, but they add to give me 0. So we're going to plug in 9m and negative 9m. So I think this has to be 9m and 9m, and this has to be positive 1, and this one has to be negative 1. And now it works. 1 times negative 1 is negative 1. So this factors into 9m plus 1, 9m minus 1. Next one, we don't want them out of order. We want to put them in the correct order first. So x squared minus 11x plus 28. So setting up the area model. My area models are getting sloppier and sloppier. So I would put x squared down here, and I would put 28 over here. So when I multiply those two, I get 28x squared, and then the middle term has to be negative 11x. So I need two numbers that multiply and give me 28, but add and give me negative 11. Stupid lights! I thought I moved earlier. All right, so I just thought of them. That would be negative 7x and negative 4x. They multiply to give me positive 28. They add to give me negative 11. So this would be negative 7x and negative 4x. Okay, finishing it off, this has to be x and x. This would be negative 7. This would be negative 4. And then negative 7 times negative 4 is positive 28. So we get x minus 7, x minus 4. I don't know if you noticed it, but on these x squared terms where there's no leading coefficient, the -7 and the -4 automatically become our numbers over here. But that only works when there's no leading coefficient, when there's no number in front out there. I don't know if you noticed on a previous example. So you really don't have to do the area model when there's not a number right in front over here. When we do these ones, we can just say, okay, what multiplies to give me 28, but adds to give me -11? It's -7 and -4. So that's kind of a shortcut you can use. You don't have to use this area model every time if there's no leading coefficient in front of the x squared. All right, now this one has a GCF on it. There is a number that goes into 3, 9, and 6. The GCF for this one would be 3. And then we would be left with n squared plus 3n plus 2. Now we factored out the 3, which is the GCF, but we still have to check to see if this leftover trinomial here can still factor. And like we were saying before, since it's missing the leading coefficient now, all I have to do is look for what multiplies to give me 2 and what adds to give me 3. And this is pretty obvious. It's 1 times 2. 1 times 2 is 2. 1 plus 2 is 3. So I can skip doing this whole box thing, and this is going to be n plus 1, n plus 2. And then the 3 is outside still. So when we factored out the GCF, this made it a much simpler problem to solve because I could skip doing the area model on that one. All right, if there is more than one factored form of part D, what were they? Okay, so what they're saying about this one is, was there more than one way to set this up? And yes, if I would have done the area model without doing a GCF, watch what happens. If I got the area model without the GCF, I'm going to put 3n squared here, and I'm going to put 6 here. So these two are giving me 18n squared. And then they're adding up to give me 9n. So what multiplies to give me 18 but adds to give me 9? That would be 3n and 6n. And so what they're talking about here is I could do, right here, I could do 3n and n. And then I would get plus 1 up here. And over here, I'd get plus 2. No. This is a 6. Okay. All right, I'm starting to lose it. So this would be 6 because n times 6 is 6n. So it looks like I could get the answer of n plus 1 times 3n plus 6. But what if I would have done it the other way? What if I would have put 3n over here and n right there? Well, then this would have been plus 3 up here, and then this would have been 2 over here. And it still works out. 3 times 2 is 6. So my other factorization of this is 3n plus 1 times n plus 2. It factors 2 different ways. So why is there more than one factored form for this? It's because this GCF of 3 on that previous problem is inside of these problems. See, this still has a GCF of 3. If we factor it out, this ends up becoming n plus 2, and the 3 would go outside. And then, this is supposed to be a 3. And then over here, I can factor out a 3 from this one, and then I'm left with the n plus 1 right there. So when we get multiple ways to get the same answer, it's because there's a GCF hidden inside of there. So we always want to get that GCF out. These are not fully factored. They're not factored completely like we're trying to do here. If you still have factors inside, they're not factored completely. So there's more than one form because there's a GCF inside of the factors. If you get your GCFs out of there, then there's only going to be one way to factor. You're not going to be able to factor it multiple ways. All right, predict which of the following expressions will have more than one factored form. We'll see how this one has 12, 10, and 2. That has a GCF in there. There's a GCF of 2. So I would predict that that one would give me more than one different type of answer because it has a GCF in it. This one, 5, negative 23, and 10. There's no GCF there. There should only be one way to do that if it's able to be done. This one, 10, 25, negative 15. There's a GCF of 5 in there. So this will give you multiple different correct answers because of the GCF. This one, 3, 7, negative 6, there's no GCF there. So these would only have one factored form. So which ones will give you more than one factored form? These two, because of the GCFs. That's why we want to take out the GCF so we don't get multiple ways of doing the same problem. All right, so we're going to factor this one completely. So we start by looking for the GCF, 2. So I can take out a 2, and I'm left with 6t to the second minus 5t plus 1. So I factored it out. If I multiply, I get what I started with. At this point, now I'm going to try to factor the trinomial after I factored out the GCF. So I set up the area model. I got 6t to the second and 1 here. So 6t to the second times 1 is 6t to the second. And they have to add up to negative 5t. All right, so what multiplies to give me negative 6 and adds to give me negative 5? Well, they both have to be negative numbers. So this would be negative 3t and negative 2t. They multiply to give me positive 6. They add to give me negative 5. So I'm going to put negative 3t here, and I'm going to put negative 2t here. Okay, so I'm going to say that this one right here has to be 3t, and this has to be 2t. And then this would be negative 1 here, negative 1 here. Multiply these, you get positive 1 right there. So my final answer for this 2 is still part of my answer. This part I have now factored into 2t minus 1 and 3t minus 1. There you go. That is factored completely. Notice inside these parentheses, there's no more GCFs in there. And that's what we want to see. All right, let's see if we can do these real fast because I need to get home. So let's factor out a 5 for this one. So that's my first step. I'm going to factor out 5, and I'm left with x squared plus 3x minus 4. Oh, it's nice. They give us a good one. So there's no leading coefficient, so this is where I can just get by with doing the diamond part. So multiplies to give me negative 4, adds to give me 3. So that should be positive 4 and negative 1. 4 times negative 1 is negative 4. 4 minus 1 is 3. So remember, when they don't have a leading coefficient here, we can just do the diamond, and then these two numbers are what we put with the x. So we do x plus 4 and x minus 1. When they don't have a leading coefficient, you can skip straight to setting up your two factors. But don't forget, we have a 5 out there that is still part of our factorization. Because remember, you have to be able to multiply this and get back to where you started. Without that 5, you can't get back to where you started there. So that 5 has to be part of your answer for your factors. Next one. 3 goes into all these, and they all have an x. So I'm going to factor out a 3x on all of these. So I would be left with x squared, negative 2x, and negative 15. Oh, this is nice. Again, I don't have a leading coefficient, which is making it easier on me. So I just have to find out what multiplies give me negative 15 and adds to give me negative 2. And I think that would be negative 5 and positive 3. Negative 5 times 3 is negative 15. Negative 5 plus 3 is negative 2. So I can say, because of these two factors, and there's no leading coefficient here, this would be x minus 5 and x plus 3. But don't forget, this is still part of our answer because we have to be able to multiply this and get back to where we started. There's no more GCFs, so we know that we've done it completely. Okay, this one right here. So on this one, I have a GCF of 2 on this one. So I'm going to factor out a 2, and I'm left with x squared minus 25. So this is the one where it's missing that middle term. There's no leading coefficient, so it's nice that we can do a shortcut on this one. So it's negative 25, and there's 5, and there's no middle term. So I need to find out what multiplies to give me negative 25 but adds to give me to 0. That's pretty easy. That would be 5 and negative 5. So since we don't have a leading coefficient, I can just take these two numbers and do x minus 5, x plus 5, but we can't forget to keep the 2. There you go. Made up a song just for you. It's beautiful. All right, last one. So for this one, there's no number here, so they don't have a number in common, but they all have a y. So I can factor out a y first. So I'm going to take out the y, and I'm left with x squared minus 3x minus 10. I've factored out that y that they all had in common. And now, since I don't have a leading coefficient again, wow, they're being really nice to us. No leading coefficient, I'm looking for what multiplies to give me negative 10, but what's adding to give me negative 3. Negative 5 and 2. So negative 5 times 2 is negative 10. Negative 5 plus 2 is 3. So now, using these two numbers, I can set up my two factors, x minus 5 and x plus 2. But don't forget, we still had the y out there. If we don't put the y here, we can't get back to where we started. So factoring completely, you have to get everything factored till it's prime, till it can't factor again. Always look for the GCF first, because you'll see in a lot of these problems, it makes them way easier to solve when you don't have the GCF in there. A lot of times you won't have to do the full method of diamond and area model. Sometimes you can get away with just doing the diamond if we don't have leading coefficients. The end. Math hard.